Welcome to today's lesson called Partial Fraction Decomposition. Now, if you've completed the investigation, you would know that partial fraction decomposition is the process of undoing making a common denominator to add to rational expressions. We're going to take a single rational expression and break it down into its partial fractions. So our first example is non-repeated linear factors. We're asked to write the partial fraction decomposition of x over x squared minus 5x plus 6. Now the first thing you always do is you factor the denominator. So we'll start by factoring x squared minus 5x plus 6. So this factors into x minus 2 times x minus 3. And then we will rewrite this expression with one fraction with the denominator of x minus 2 and another fraction with the denominator of x minus 3. Now when you have a linear factor in the denominator, we're looking for a constant in the numerator. So I'll put a constant a here and a constant b here. Now our job is to figure out what a and b are. So the next thing, after we have set up the decomposed fractions, we need to simplify this equation by multiplying both sides by the LCD. Well, the LCD is x minus 2 times x minus 3. When we distribute this over here, we cancel, so we're left with x. When we distribute this over here, the x minus 2's cancel, so we have a times x minus 3, and when we distribute here, the x minus 3 factors cancel, and we have b times x minus 2. Next we simplify by distributing, so we get x is equal to ax minus 3a plus bx minus 2b. Now, in order for the left side to equal the right side, the terms with the same degree have to equal each other. So what we're going to do is we're going to say that in order for this to work, x will have to equal ax plus bx. And since there is no constant on the left side, 0 is going to have to equal negative 3a minus 2b. So the way I'm going to set this up is I'm going to say we'll take the coefficients of the x terms and set them equal to each other. So the coefficient of x is 1, and coefficient of ax is a, and the coefficient of bx is b. And then we're going to look at our constants. Well, we have no constant on the left, so we'll set that equal to 0, and 0 has to equal negative 3a minus 2b. So now we have a system of equations to solve. We have two equations and two unknowns. We can say then that b is equal to 1 minus a. Substitute into the second equation, so 0 equals negative 3a minus 2 times 1 minus a, or negative 3a minus 2 plus 2a, which leads us to 2 is equal to negative 3 plus 2a, or negative a, which means a equals negative 2. We substitute this into this equation and we get b equals 1 minus negative 2, which is equal to 3. And then finally we substitute in a and b into our original decomposition that we had above, and we can say then that x over x squared minus 5x plus 6 is equal to negative 2 over x minus 2 plus 3 over x minus 3. Example 2, repeated linear factors. Write the partial fraction decomposition of x plus 2 over x cubed minus 2x squared plus x. So we need to factor the denominator as always, and first we're going to take out the GCF, which is x, and we're left with x squared minus 2x plus 1. Well, this is a perfect squared trinomial which factors into x times x minus 1 squared. So notice that x minus 1 squared is a repeated linear factor. So we have to handle this a little bit differently. When we decompose now, we'll say that this is equal to a over our first linear factor x plus b over our second linear factor x minus 1 plus c over our repeated linear factor. So keep in mind, when you have a repeated factor, you write it once to the first degree, and then you write it a second time to the second degree. The next step would be to multiply both sides by the GCF, which we know is x times x minus 1 squared. So this makes the left side of the equation turn into x plus 2. When I distribute this over here, the x's cancel, and I have a times x squared minus 2x plus 1. When I distribute it over here, one of my x minus 1 factors cancel, and I am left with bx times x minus 1. And when I distribute over here, my x minus 1 squareds cancel, and I have plus cx. Now I have to simplify by distributing. So I have x plus 2 equals ax squared minus 2ax plus a plus bx squared minus bx plus cx. So now my highest degree is x squared. So I'm going to write three equations. I'm going to have my x squared, my x, and my constant. So there is no x squared on the left, so that means 0 has to equal a plus b, my coefficients in front of x squared on the right. I have 1x on the left, so 1 has to equal negative 2a minus b plus c. And then finally my constant is equal to 2, and 2 has got to be equal to a. Oftentimes it's okay for us to use our calculators and matrices to solve these equations, but this one isn't that hard. We know that a is equal to 2. If a is equal to 2, then 0 equals 2 plus b, which means b equals negative 2. And then finally 1 equals negative 2 times 2 minus negative 2 plus c, or 1 equals negative 4 plus 2 plus c, which means then that c equals 3. So we'll put all these together by plugging back into what we've written up here, and our final answer was going to be this: x plus 2 over x cubed minus 2x squared plus x is equal to 2 over x plus negative 2 over x minus 1 plus 3 over x minus 1 squared. Example 3, non-repeated irreducible quadratic factor. So we're going to write the partial fraction decomposition of 3x minus 5 over x cubed minus 1. So we start by factoring the denominator. Well, you might recognize that x cubed minus 1 is the difference of two cubes, so that factors into x minus 1 times x squared plus x plus 1. Here we have one non-repeating linear factor and one non-repeating irreducible quadratic factor. So we're going to now decompose the fraction, so we can say 3x minus 5 over x cubed minus 1 is equal to a over our linear factor x minus 1. But remember when I said that the degree of the numerator is always one less than the denominator, so with a linear factor we have a constant in the numerator, but if we have a quadratic factor in the denominator, that means that the numerator has to be linear. So I'm going to write this as bx plus c. Now that we have decomposed the fractions, we'll multiply both sides by the GCF. The left side becomes 3x minus 5. When I distribute over here, the x minus 1's cancel, and I have a times x squared plus x plus 1. Here, the x squared plus x plus 1's cancel, and I've got bx plus c times x minus 1. Now we'll simplify. So we have 3x minus 5 equals ax squared plus ax plus a plus, if I FOIL, I get bx squared minus bx plus cx minus c. Now that we've simplified, it's time to match up the degrees on both sides. We have our highest degree is x squared, we have x, and we have a constant. On the left side, I have no x squared, so that will be 0, and that's going to be equal to a plus b. On the left, I have a 3x, so the coefficient is 3, and on the right, my coefficients in front of x are a minus b plus c, and finally my constant on the left is -5, and my constants on the right are a minus c. Now this is a more complicated equation in 3 variables, and so it's totally okay to write this as a matrix equation and use your calculator to solve. You should still show how you put it as your matrix equation. So my matrix equation is going to look like this. It's going to be 1, 1, 0, c, 1, -1, and 1, and then a 1 and a 0 for b, and a -1 times a, b, c has to equal 0, 3, and -5. The solutions will tell me now that a equals -2/3, b equals 2/3, and c is equal to 13/3. Not the prettiest solution I've ever seen, but it is okay for these coefficients to go in as fractions. So our final answer is going to look like this: -2/3 over x minus 1 plus 2/3 x plus 13/3 over x squared plus x plus 1. Our last example, example 4, is repeated irreducible quadratic factor. So we're going to write the partial fraction decomposition of x cubed plus x squared over x squared plus 4 squared. So notice that x squared plus 4 is not factorable, which makes it non-reducible, and it is also repeating. So fortunately we are already factored, so we get to skip that step. So let's just go ahead and rewrite this out, and we're going to have our first quadratic factor raised to the 1 degree, and then we're going to add to that our quadratic factor squared. Now because these are quadratic factors, the numerators have to be linear. So we'll have ax plus b plus cx plus d. The next step is to always multiply both sides by the LCD, giving x cubed plus x squared has to equal ax plus b times x squared plus 4 plus cx plus d. Now I'm going to FOIL, and I'll get ax cubed plus 4ax plus bx squared plus 4b plus cx plus d, and that's equal to x cubed plus x squared. Now this is actually in 4 variables, so you might think that we're going to want to use matrices to solve this, but I think this one's going to wind up being pretty simple. We're going to have x cubed, x squared, x, and our constant. Our coefficient in front of x cubed on the left is 1, and that has got to equal a. Our coefficient in front of x squared on the left is 1, and that's going to have to equal b. We don't have a coefficient in front of x, so 0 has to equal 4a plus c. And we don't have a constant on the left, so 0 has to equal 4b plus d. Now I can go ahead and plug in a 1 for a, and I get that 0 is equal to 4 plus c, which means c equals -4. And I can plug in a 1 for b, and I get 0 is equal to 4 plus d, which means d is equal to -4. So my final answer is going to be 1x plus 1, or x plus 1 over x squared plus 4 plus -4 4x minus 4 over x squared plus 4 squared. And that's all for now. Thanks for watching.